Okay, so with the last video, we looked at finding the solution of this particular differential equation. And like I said, the focus is not on how to solve at this point, but just kind of some of the properties of the solution and what it means. So we found the solution was ce to the negative x squared. So now suppose that we modify the problem so that it says solve the initial value problem where the differential equation is the same. I mean, I'm using the Leibniz notation for the derivative, but it's just the same ODE. But now I've got this additional initial condition added in. Okay, so the differential equation part is still the same. So we still have that y is ce to the minus x squared. But now let's see, we'll substitute in x equals 1 and y equals 2 into this equation right here, and then that will allow us to solve for c. So we have y is equal to 2, and when we take the formula for y and we substitute in x equals 1, we have ce to the minus 1 squared. So that's ce to the minus 1. So we can solve for c just by taking the e and multiplying both sides of the equation by it, thereby moving it over to the left. And we get that c looks like 2e. So putting that back into our equation, we have y equals c e to the minus x squared, or if you like, e to the 1 minus x squared. So there is our solution to the initial value problem. Okay, so let's talk a little bit about what happened right here. So last time I said that we have the general solution, and that any choice of c gives a particular solution. So those are the two terms that I'm interested in, general and particular solution. So I also said that the general solution is a one parameter family of solutions. And the meaning of this is best illustrated by this particular picture right here. So here we have the one parameter family of solutions, ce to the minus x squared, and then a particular c is chosen via an initial condition. So let me just recall the definition for that there. So an initial condition this is going to be an equation of the form y of 0 equals b, where b is some number. So if you haven't seen this notation before, this right here, all this means is b is a real number. So it basically means that there's no constraint on b at all. It doesn't have to be an integer, it doesn't have to be positive, whatever. It's just any real number. The little, this boldface r right here, this is the set of all real numbers. And this funny little e-looking thing just says that it's an element of that set. So, okay. And more generally, it doesn't have to necessarily be the case that your initial condition is at 0. Sometimes initial conditions are given at some other point. So for example, we were given the initial condition that at 1 it's equal to 2. And so that particular point is right here. Here's the initial condition. So if you look at the general solution is this entire family of curves. It includes, well, that was a terrible one, but it includes all of these curves that have this formula for some value of c. And when I choose an initial condition, I'm saying I want the curve, the member of that one parameter family of solutions that passes through this particular point. And so that, in this particular case, isolates this blue curve here that we have that comes up and then down like that. So that's the one that we get from this initial condition. So just to, whoops. So just to emphasize that there, the the initial condition algebraically determines c, the integration constant, and more geometrically, the initial condition selects the particular solution yp that we want for this initial. That's the solution to this initial value problem.